Hi guys. Today I'm going to be talking about long context transformer models. First, I'm going to give an introduction of myself. I work at Cohere on the pre-training modeling, pre-training side, and with a special focus on long context transformer models. First, I'm going to give an introduction of a very brief introduction of transformer models, and also the current status of long context transformer models in general, and what are some of the challenges we're facing for training, evaluating the current transformer models. I'll dive deeper into the challenges we're facing right now, and also the possible solutions we have. And I'll also specifically talk about inference for long context models for a bit. And then in the last I'll give some pointers, some of the thoughts on what are some of the improvements we can do given the current status of long context models. So first, I'll give a very brief overview of transformers and also the long context models. So on the top right corner, there's a picture you probably have seen many times when you're reading papers. There's this the standard transformer model, the attention part of the transformer model. You map the input to queries, keys, and values, and then you perform attention between the queries and keys. And then on the bottom left corner, you have a attention matrix, which is it's the product of the queries and keys. And if you visualize the attention matrix with a causal mask, which is what most transformers use, you're going to see all the bottom left triangle of this attention matrix will be needed to be computed by the accelerators. To give an overview of the long context transformer models, most of the transformer models, open source or closed sourced, they can support context lengths from 128K tokenized sequence to about 1 or 2 million tokenized tokens. Those models including Command R, R+, GPT-4, Gemini, and Claude, and etc. Text tokens can be tokenized into about 100K to a few million tokens, depending on the input source you choose. They can be books, novels, or papers, which all fall into this long context domain. And there's also multimodal data, which is, can also be very long. For example, each image can be tokenized with some kind of image tokenizer into a few hundred tokens. And if you have multiple images combined with text in a corpus, the entire sequence can be long. And with other modalities like video and audio, the tokenized lengths can be even longer. So that is kind of the background of long context transformer models, why we need long context, and what are some of the currently supported models that support long context. One of the challenges we're facing for training, evaluating the long context models is the multi-head attention part of the well-known transformer architecture. The multi-head attention is n squared complexity, with n being the sequence length of the input tokens, like what is showing on the bottom left corner. So I'm gonna dive deeper into the challenges we're facing for building long context transformer models. There are 4 of them I want to discuss: position embeddings, memory and computation, data, and evaluation. The first thing will be position embeddings. So for position embeddings, we have the original sinusoidal position embeddings, rotary embeddings, the T5 bias embeddings, and also alibi embeddings that basically they model the sequentiality of the input tokens. And what we currently observe for almost all of the position embeddings is that position embeddings don't extrapolate well beyond your training lengths. So if you look at the graph within the training length, this is a model trained with 10K tokens. So within the 10K sequence range, you can have a good perplexity from the model. But if you extrapolate beyond the training length, most of the position embeddings just like explodes in terms of perplexity, which means it's not able to even give a coherent answer starting from around the 1K, 2K sequence range. So that's one of the major bottleneck for scaling transformers to longer context lengths. We have some solutions with respect to the extrapolation of position embeddings. We have something which is usually referred to as NTK scaling on this particular type of position embeddings, rotary position embeddings, which basically we can scale like one hyperparameter of rope from what is the default setting is 10K to a few million or even like 1 billion, depends on like different like model, what different model uses. We have like code llama, E large, command RR plus, and the gradient model, which all like use this method to scale to above 128K sequence length. And this rope scaling method actually affects both pre-training and post-training. And there are some researches done with respect to this, which I listed on the bottom as references. They talk about how this scaling factor, this rope theta scaling factor, affects the model performance on both pre-training and post-training. And another thing we always observe is if you want to have good performance on longer context, you should always aim to train at a longer context. So training on like longer context data actually helps us improve long context performance compared to like only use rope to scale the context length to like a higher to longer tokens. So I listed some of the references below to talk about like NTK scaling, context length scaling, and scaling laws of rope-based transformer models. And the second challenge we have is memory and computation. So when we train transformer models, we need to overcome this this attention matrix bottleneck. If you look at the top right corner, the attention matrix always has computation complexity of n squared, which is sequence by sequence, and this is it becomes very expensive when you scale to longer sequence lengths. So here I did an experiment by setting the batch size to 1 and use bflow 16 as a precision and some dimensions, which is like a very standard llama 2 hyperparameters choice, like head dimension 128, number of heads 64. And by scaling from sequence length 8K to 256K, we can see on the bottom left is the memory requirement for storing the queries, keys, and values in memory. And we can see on a single device with 256K sequence length, you need 4 gigabytes on a single device for a single batch size to be stored in the GPU or like the accelerator memory. And if you want to store this n squared matrix in memory, it's going to take much more memory. It's going to be quadratic in terms of the sequence length. On the bottom right, the graph at the 256K sequence length, you actually need 60 gigabytes to store this entire n squared matrix into memory, which is like a lot, given what we have for the current accelerators. Like H100s and A100s has only 80 gigabytes of memory available. So this will become a bottleneck when you want to train for longer context models. And computation as well. Computation scales quadratically according to sequence length as well. So theoretically, a 128K model actually in theory, it has like 10Kx more compute compared to a 4K sequence length model training. But because we are using accelerators to do training, the actual numbers will actually be less. The ratio will be less, but still it's substantial compared to like short sequence training. So some of the solutions we currently have to solve this memory and computation bottleneck is that first we have flash attention, which is like kind of like well known. So the idea of flash attention is we don't materialize the attention matrix, or like we don't materialize anything related to the attention, like whether it's the attention matrix or the bias. So this is kind of well known. So I'm not gonna go deep into details into this. We also have some other methods that's less well known, but works really well and very specific to long context. And also something we experimented internally to improve long context training. Those are ring attention, or like sequence parallel methods in general. And also we can exploit the sparsity of attention. And one of the methods I'm going to introduce later is a sliding window. So first I'm going to give a brief overview of ring attention and the idea of ring attention. So the general idea of ring attention is given a input sequence of like a certain length, we can shard on the sequence dimension. So in the graph here, we're actually sharding the input sequence into 4 different GPUs, and for each of the sequence, it's getting 1/4 of the entire sequence length. So all the queries, keys, and values will also be sharded into 4 different GPUs. So this way, we effectively reduce the memory requirement of storing the queries, keys, and values into by the number of sequence parallel shardings. This is something, and then we can apply the idea like similar to flash attention, which is in flash attention we don't visualize this n by n squared attention matrix, and in this ring attention it's very similar. We don't materialize the entire n by n matrix. Every time we do a computation, we compute locally the product between the queries and the local keys and values. And after this, and in the meantime, we can do a communication across the GPUs in a ring fashion. So in this graph, we're going to pass the keys and values from GPU 1 to GPU 2, and we're going to pass the keys and values from GPU 2 to GPU 3. So we're going to do a ring fashion to like move the keys and values around. And we're going to do this 3 times in this case, and do 4 times, do the local computation 4 times, and aggregate the results. So this way, we don't visualize the attention matrix, and we can also shard the inputs on the sequence dimension. So that's like the general process of ring attention. The benefits is, one is that we can do the key values communication along with, at the same time with computation. So like when we are computing, we're also moving the things at the same time. So we're hiding the communication cost behind the computation. Another benefit is that we can actually scale to arbitrary sequence lengths by just scale the number of devices. So let's say we're training on 128K sequence lengths. We're doing like a 16 sequence parallel sharding. If you want to scale to like 2x the sequence length, you can just use 32 devices. Basically, it's linear in terms of the devices, and the memory bottleneck on each of the devices will remain the same. So that's like an overview of the ring attention approach. This also combines well with the feed-forward computation. So after the attention computation, the transformer has a feed-forward layer. And because we're sharding each of the device, we're sharding the input sequence to based on the number of device. So when we are doing the feed-forward computation later, we can do it simultaneously based on like within each device without any extra communication, because this feed-forward operation is independent of the sequence dimension, which means by doing this ring attention, we don't actually, like theoretically, we don't incur any communication overhead, which is very efficient. And last approach is a sliding window. this idea comes from for a lot of times the attention are actually sparse, which means we don't have to attend to all the tokens from the history. We can choose to exploit like certain levels of sparsity from the attention. Like in the example here, comparing to like what we had before, we have this this causal attention matrix where we attend to everything that's on the bottom left triangle. Here we can choose to attend to only the local windows. Like for every token, we're attending to like in this example like only 3 tokens that are in the proximity of the query tokens. And if you design the framework properly, it can actually speed up training and your memory, speed up training time, and also improve the memory overhead. So in terms of the complexity, if you look at the graph, we're actually only computing, for each of the queries, we're only computing the number of tokens that are equal to the window size. So let's say you're doing a 128K sequence length training. Your computation complexity, like theoretically, should be 4K times 128K. Instead of like if you do like a full-on causal mask like this, you're gonna have 128K by 128K as the computation complexity, and this will give a 32K theoretical improvement over the dense attention approach. But this method requires you to write the kernels efficiently to be able to exploit this sparsity. So it poses some engineering, some extra engineering work. And that's for memory and computation. And next, I'm going to talk about data. Data is also a very important factor for training and evaluating long context transformers. So first thing I'm going to talk about is the data mixture. Data mixture is very important for a transformer model, especially the pre-training data mixture is important for the basic capability of the transformer model. Tuning this mixture can actually have a huge impact on the evaluation, on the performance of transformers. So to train a long context model, usually we have 2 kinds of data. First is the long text data. That is mostly like includes like books, paper, and also repository level code that can scale to like longer context than 128K from those sources. And we also have multimodal data, which like I discussed at the very beginning, each image can be processed into like a few hundred tokens. And also video and audio modalities can even like scale the context to be longer. So the issue with long context data is that the data distribution, if you only train on the longer context regime, the data distribution is actually super skewed compared to like your pre-training data mixture, which leads to a suboptimal model capability if you like naively scale up the data distribution in the longer context range. And also long context training can be slow because of even if you use like ring attention or flash attention or any of the kernel optimizations, like in the end you need to have some kind of you need to compute the n squared attention matrix, even if like you use like the kernels. So long context training is always like slower than short context pre-training. So some of the solutions we have for this is we can interleave short and long context training, and then set up a corresponding proportion to each of the data mixtures. This also requires some infra work, but this can help balance the data distribution, and also we can have a trade-off. By setting the data distribution, we can have a trade-off between short and longer context training time. We can also try to use scheduled or curriculum training, which basically means we train the transformer first on a shorter context, and then we slowly scale to longer context. Like first we pre-train on 4K, scale to 32K, and then to 128K. This is also some very general practice for scaling transformer to longer context. We can also experiment with data packing, which means we're going to pack both the short examples and long context examples into like a certain sequence length to speed up training in general. And also, long context data is comparatively scarce compared to short context data. And long context annotation is also difficult for human labelers. So imagine you're labeling for the instruction tuning data with like a single paragraph or maybe a short sentence. That's relatively easy for human labelers to do. But if you're asked to like to give some question-answer pairs or label like an entire essay or like an entire book, that requires a substantial effort from the human labelers, and it's not very scalable. So based on this, we need some synthetic data to help us balance the data mixtures. Long context synthetic data is also difficult to generate compared to like short data, but there are some solutions, existing solutions on how we generate this. I'm not gonna go into details, but I linked the paper, which is a research done by Meta, about like the practices. And there are also some questions of generating long context preference pairs, or like on the preference or like a reinforcement learning domain. It's really hard, difficult for the model to synthetically generate preference pairs, and also to train a reward model based on the synthetic long context preference pairs. And also online preference training, like RLHF with long context is also a hard problem. So those are kind of like the problems yet to be solved by the industry. We currently don't have, to my best knowledge, we currently don't have a scalable way of producing the training data and also have an efficient paradigm to follow to train with preference training on longer context. And the last thing I'm going to talk about is evaluation. So similar to the data problem, we don't have, the first thing is we don't have enough data. We don't have good data to evaluate our longer context models. And also we don't have a good metric, like a lot of the traditional metrics, what we usually use, like perplexity or BLEU or RU scores, fails to indicate whether this long context model has a good performance or not. There are a lot of researchers that have like discussed that point. So the solution will be we want to use synthetic evaluation. Some of the synthetic or like partially generated synthetic evaluation benchmark are like the well-known needle in a haystack, a more complex version of needle in a haystack, which is called ruler, and also some other evaluations like long bench. I'll give an example of needles in the haystack. This is like a partially synthetic data where you have a bunch of essays and you concatenate all the essays into like a long corpus, and then somewhere in the context you're going to arbitrarily insert like a sentence into this entire corpus. Like in this example, we're inserting the best thing to do in San Francisco is eat a pizza, and you're going to ask the model at the very end, what is the best thing to do in San Francisco? So you're basically asking the model to retrieve from a synthetically generated corpus to retrieve a certain fact and to test whether the model is able to get it right. So that is kind of like the it's mostly used for like all the long context evaluations like GPT-4, Claude. If you publish a paper, it's very easy to see this kind of evaluation appear in the long context session of the paper. And last thing I'm going to talk about inference. So for inference, long context also poses a challenge on inference because in the inference phase, we need to prefill and also we need to decode. So prefill is kind of like you have a context and you need to produce the KV cache of this conversational history. So this is very similar to training. It's n squared computation. It's basically the forward path of training. And the decode part is the major bottleneck. We have KV cache. which is I did some like rough calculation with bflow 16, and we're saving both keys and values. With the like a similar setting to Llama 3 8 billion, we have about 20 gigabytes for a single batch size, like a single device, and that is pretty huge. Given 128K sequence length, that is pretty huge. And also decode speed can be slowed down when the KV cache is big. There's a lot of memory movement when you do decoding, like between the GPU memories and your cache, and there's less computation. So this is something we want to optimize. I'm going to briefly introduce our prior work on this, which is called the SnapKV. It's a collaboration between Cohere and UIUC. We try to exploit the sparsity of KV cache to basically compress. Let's say you have like an entire conversational history. We're trying to compress the tokens based on like the attention scores. And then, so when at the pre-filling stage, we're selecting from the conversational histories. And in the decoding stage, we only need to attend to like this, let's say 100 tokens we selected instead of the entire conversational history. And we can achieve a 32K KV compression ratio with basically lossless needles retrieval. If you look at the bottom right, we tested this SnapKV method on Command R. We're able to compress the conversational history from 128K to 4K with only 0.5% difference in the evaluation benchmark, which is basically lossless. And there are a bunch of other work on this to sparsify the KV caches, which is like also like more or less efficient. Yeah, I listed the link of the paper in the presentation slide. Last, I'm going to talk about some of the future work that I think are worth looking into. So first thing is position embeddings. We may need more efficient or like a better way to model the position information of the context. The next thing will be also something popular, but I didn't cover in my presentation, which is SSMs, structured state space models, or like or maybe explore some hybrid architecture between transformers and those RNN style architectures. There are also explorations to improve the attention module. For example, the MLA architecture by DeepSeek, which is also interesting. And to explore the hybrid architecture, we need better framework and better infra support to be able to train and evaluate the models efficiently. On the data part, like I said, the long context preference domain and also reward model training is very hard. It's a very difficult task right now. We haven't been able to solve it with synthetic. We have some explorations internally, but we still need an efficient paradigm like what we have for the instruction tuning domain. Maybe we need a different paradigm for long context model. Maybe preference data or like preference training is not the best way to scale transformer models to longer context. That's something we need to think about for future work. And on the inference side, dynamic KV compression is something we are interested in exploring. So all the compression algorithm, like SnapKV, like everything else we showed so far, is static compression. That means you're asking a question and the model compresses the history based on the question you asked. But if you ask another question that is of like a completely different topic, then we're gonna either need to recompute the cache, or we need to do something else to make the cache or work for the new question. But that will make the kind of defeats the purpose of saving compute and memory. So this dynamic KV compression is I think will be the next big movement for long context inference. And yeah, that will be all about my presentation. Thank you guys for listening. Yeah, if there's any questions.
We're tight on time. We have one quick question, unfortunately, but go ahead.
The question was about compressive memory, because like a lot of the stuff that you seem to be doing with KV cache is filtering out the tokens that haven't been attended to. But I would imagine that wouldn't work if you changed topic or you suddenly were asking things that the attention is the tokens that have been filtered out. What the Google Infini attention thing uses, like as the KV cache goes off the end of the context, uses compressive attention, so like an RNN style mechanism that passes that information forward, and that's how they're able to do constant time, so n with the context length. Have you guys looked at using something like compressive memory, and is that what you mean by dynamic KV compression, or is KV compression for you filtering out the tokens and not the state that's passed forward?
I think you're exactly correct. That's what we mean by dynamic compressing. But the Google Infinity attention is kind of like you have an attention module, and then you compress all the history into this attention module with some kind of training. Like RNN style, you have a hidden states, or like some kind of training, right? But that will, first thing is it's a slightly different architecture than the standard transformer, which requires you to do everything differently from the pre-training stage to like instruction tuning, preference tuning, and whether it's like it's going to have like a different performance on the general model capability is a question we need to test before we actually put it into production. But I think it's an interesting direction to try, and it's also like a general like question whether the RNN style model is actually able to retain the transformer base capabilities, like retain the same capability as the transformer model, and then be able to like reduce computation, reduce the memory, and also scale to longer context. That is kind of like a bigger question to ask for the industry, and whether it performs as well when it scales to more parameters like transformers. Yeah.
One more round of applause for first talk.
Thank you.
Thank you very much.